Good afternoon, everyone, and welcome to the 31st meeting of the Facet Faithful. Glad to see you all here. What our subject is today is essentially my vision for what could be a better personal aircraft than the ones we've been quite successfully building for many decades. I'm Barnaby Wainfan. I'm an airplane designer, a hardcore EAAer, and as of not too long ago, I can count 30 new airframes that I've worked on, including, of course, the subject of today's talk, the Fasmobile, and what hopefully will follow. So what is this really all about? What it's about is a better airplane for the way private pilots fly, a personal airplane. Now, that's not really that easy a thing to do because all the designers of all those wonderful machines you see right out there did a damn good job. You know, conventional airplanes have evolved to where they're very good airplanes. So for me, I wanted to look at an alternate approach to see what could we do better. And the answer isn't, to me, refining conventional airplanes, not because there's not gain to be had in that, but because to get the kind of changes I was envisioning, you have to do something different. And also, for me personally, that was a more fulfilling thing to do. So, you know, before you start out to do something, you got to figure out what it is you're really trying to do. And so in that way, we can look to history, we can look to the concept of revealed preferences. And a revealed preference is what you determine from watching people's actions rather than what they say. So for this example here, what kind of airplanes do private pilots really buy? If you compare just production numbers, you look and you see that in 50 years, Beechcraft built about 3,000 Bonanzas. In somewhat less time than that, Cessna sold 37,000 172s. And these are old numbers. They're still, they're still building them. Now, if you had no worries about money and you could afford an instructor to teach you how to fly it, and someone's just going to give you an airplane, I'll take the Bonanza. I think everybody would. The 172, however, sells so much better because it's good enough for the resources and the skills that private pilots really have. They can afford it, they can fly it with modest skill, it's fast enough and has enough useful load to fly the kind of trips they want to fly, and while it is the opposite of sexy, it's a very good airplane. Because how are we really flying? I mean, think about it. Most of us, most of the time, are taking relatively short average flights. We're going for the $200 hamburger. Inflation is a bitch. And we're flying like sightseeing or VFR operations most of the time. I mean, some people fly IFR, some people travel, but most of us are flying VFR. We're operating out of smallish airports. My home airport in Independence, Oregon is 3,000 feet. You want an airplane that you can routinely fly out of about that length airplane without worrying about takeoff and landing and whether your technique is spot on perfect. And sport airplanes are flown by private pilots. And the reason I put that in there is because the designer has to take into account the level of skill and proficiency that the operator of the airplane is really going to have, not what they're supposed to have and not what they aspire to have. And cost is important. Cost is always important, no matter what you're buying and no matter where you are in the market. But at the bottom end, where it's private individuals buying things, cost is even more important. So what do I really need in a personal airplane? I got to be able to afford to buy it, first of all. It's got to be safely operable with modest pilot skill. It's got to have good enough performance, enough useful load to actually carry who you want to carry. And by the way, that's a significant issue, and we'll be discussing more about that in a moment. And a comfortable enough cockpit environment, and cabin size is a real thing. I have a 1975 Cessna 150, which I dearly love. It's a great little airplane as long as you don't expect it to be anything but a 150. But I get in there with another full-sized adult, even someone I care about, and it's a good thing we like each other. Now, useful load. It's increasingly an issue, and not just for light sport. And blessings be upon whoever in forming the Mosaic requirements took off the gross weight limit. God bless them. They saved us an awful lot of pain and made an awful lot of airplanes more usable, and that is a wonderful thing. But back when Part 23 was originally codified, the FAA standard adult was 170 pounds. Well, what does the data say now? Go look at demographic data, anthropomorphic data for the United States, and the median weight for an American male in the middle age range is 195 pounds. That means 50% of American males weigh more than that. When you go to 75th percentile, it's 227 pounds. What does that mean? If I take two 75th percentile men and 25 gallons of avgas at 6 pounds per gallon, I'm at just over 600 pounds useful load required. And not many of the legacy trainers really carry anywhere nearly that much. My 150, for example, has about a 520 pound useful load. So that is increasingly a problem. Now, I did have an incident years ago with a side-by-side two-place airplane that I had helped design, the Kolb Extra, where they had someone called in and said he liked his airplane a lot, but he was having real trouble on a final approach because he was running out of elevator. Well, it was a pusher, right? So the CG moves forward as you load it. And so, the president of Kolb asked him, well, how much weight did he have it? He was a good old boy. So I said, well, I don't rightly know, but I'm about 325, and Billy Bob, he's a big boy. So, no matter what kind of load you put in the airplane, somebody's going to overload it. But fundamentally, what this says to me is that for a two-place airplane in today's world, you want to target a useful load of at least 600 pounds. And you've also got to be able to afford it. And the fundamental reason for that is that private airplanes are purchased with discretionary income. It's not a business investment. It doesn't pay for itself. And so you have to fit in the market where people can actually afford to buy it. Well, to me, one surrogate for that, just to look at it was an interesting thought experiment, was to say, okay, let's look at cars. Because everything from, say, the Toyota Corolla up in luxury is people spending discretionary income to indulge themselves. So, I put forth the notional idea that if I could sell a two-place airplane for about the price of a high-end production luxury car, not a hypercar, I should be able to sell a lot of them. Well, it's an interesting thing, because if you go back and look, in 1973, when I got my pilot's license, a brand new, at the factory, Cessna 150 cost about $13,000, and a brand new Cadillac Sedan DeVille, which was the top of the line Caddy, cost 12 grand. Somebody making the decision at that time could say, you know what, we'll drive the old car another 5 years and buy the airplane. Now you roll the clock ahead to 2006, which is the last time I looked at it, and suddenly, 150 isn't in production anymore, so the Diamond DA20 was the closest thing available. That's a pretty steep price, but look at what the Caddy cost. So suddenly it's 2-3x. And guess what? They're not selling very many airplanes. And I used to have a chart in this presentation, which I've taken out, but you can correlate it. I actually went back and did the numbers. And for Cessna 150s, as long as the 150 cost no more than 125% of the cost of a high-end caddy, they were selling 1,000 airplanes a year. As soon as it exceeded 150%, the bottom dropped out. So that gives you kind of an idea from an affordability where we want to aim. Is that doable? I don't know. But that's kind of a target, something to think about. Now, when we get into safety, remember, this is not combat. There is no fundamental reason to be risking our lives to have a good time. We're out there flying for fun, right? I mean, there's a few adrenaline junkies out there that's part of the thrill, but not most of us, I hope. So 2 quotes to go with that. The first, obviously, from the RAF, that when a prang seems inevitable, strike the softest, cheapest object in the vicinity as slowly and gently as possible. And then the wonderful quote from Max Stanley, was Northrop chief test pilot, so he understood dangerous airplanes because he was the one who put the first flights on the original Northrop Flying Wings and the P-61 Black Widow, that the Cub is the safest airplane in the world because it can just barely kill you. So when we look into this a little bit deeper, you know, there's that old saying that takeoffs are optional, landings are mandatory. And once I'm airborne, there are many possible outcomes to that flight. Now, we all hope for the normal, safe arrival. We go to where we intended to fly, land, taxi in, tie the airplane down, life is good. What happens if the conditions start to get bad or the airplane starts to deteriorate? I see the oil pressure dropping, something like that. If I can make a safe precautionary landing at any airport, still a good day. Next step is a forced landing. Say the engine fails on me and I'm able to put it down on a road or in a pasture and the airplane's intact and I'm intact. Great. I'll take it. Now, then things start getting progressively worse. If a crash is inevitable, if you can damage the airplane but not the people, it's still a good day. Sometimes it will take you a while to realize that if you go through such a thing, because your mind plays the what-if scenarios. But if in the end all that's broken is hardware, we count our blessings and move on. And from there it gets progressively worse to unacceptable. The thing that is interesting about every one of the acceptable outcomes is the pilot has to maintain control of the airplane until it stops on the ground. If the pilot loses control of the airplane, the odds of a safe outcome are very small, whether that's a stall spin or disorientation in flight or anything else. So from a design viewpoint, this is the really important thing. The pilot needs to maintain control of the airplane. And the fundamental reason for that is this. This is what we affectionately call the curve of doom. And what this is crash data and survivability from SAE research. And the way this is plotted, the y-axis is the impact angle between the uncontrolled arrival and the ground. And the x-axis is the speed you're going when you get there. Now, there's a lot of insight in this curve. Because the first thing that really gets to me is this number right here, about 77, 78 knots. Flat impact, still likely to be fatal. Which is interesting, because as airplane people, we don't think of that as very fast. But it's really over 90 miles an hour. And so if you say, okay, look, I'm going to just strap you in your cockpit and drop you in a random spot you don't get to pick with no control at 90 miles an hour, that's pretty scary when you think about it. The other thing that is interesting is it tells us that the regulators, as much as we don't like them sometimes there is great wisdom to be gotten from why they chose certain numbers. So if you look, for example, up here at 45 knots, which was the clean stall speed for LSA before Mosaic. 90 degrees, which means unless you fly into a brick wall, you'll probably live through it. Just to explain this curve a little more, this side is dead, this side is alive. This side does not mean you walk away. It means you can be dragged from the wreckage in repairable condition. You know, but you'll survive. Now we have, in Part 23 and also Mosaic, we're now up in the 55 to 60 knot range. Stall speed. Now, what that means is I'm going to approach, let's say I lose my engine. I'm going to approach it sometime around 1.2 times that stall speed because I want to keep up a little margin, which puts me out here at 65-ish, 70 maybe. I'm still on somewhere a 10 to 20 degree slope. If I keep the airplane under control and glide, It's going to be shallower than that. So pretty good odd, once again, as long as I don't hit a really nasty obstacle, that's a survivable situation. That's a formula for a safe forced landing, or at least a survivable one. But once again, to hit slow and flat, you have to maintain control of the airplane, because what kills people in stall spin accidents is the near vertical impact. So once again, if you can maintain control of the airplane, control of the descent slope, your odds are pretty good even when things get pretty ugly. Now, in service of that goal, we have to look at pilot skill, because once again, people are flying private pilots, and you know, most of us, most of the time we fly are not out there doing proficiency work. We're enjoying the fact that we got to go fly. You know, we do proficiency air work occasionally, check rides, flight reviews, maybe some of us go and play with it a little bit a couple of times a year, but fundamentally, we're just out there flying around. Stall spins are still a big deal. They're still a significant portion of the fatal accidents. So what do I want? I want docile, predictable flying qualities. I want the airplane to warn the pilot, hey boss, I don't like this, without jumping out from under them. Because from a designer's viewpoint, we need the airplane to save the pilot, because we cannot count on the pilot having the skill to save the airplane. I mean, you know, there's this great law of mechanical engineering that for every idiot-proofing method, there exists an equal and opposite idiot who will end up operating the machine at the most inopportune time. And so I've concluded we can make things full resistant but not idiot-proof. And the goal is to be full resistant. That is, somebody who's a little behind the airplane, not maybe up on his on their proficiency as much as they should be, that the airplane will be forgiving enough that they won't die in that airplane. So in service of that goal, how do we get there? Well, what most people have been doing for a long time is trying to improve conventional airplanes, and done a damn good job of it. And, you know, there's still incremental gains to be had. Composites are getting better, laminar flow wings, leading edge, discontinuous leading edge cuffs, which actually help stall spin resistance. And one of the things that I am a passionate believer in is full vehicle parachutes, BRS. And, you know, the BRS is a really interesting thing in terms of technology, because it's one of the things that started in the crazy experimenter community and went mainstream. You know, usually it's the other way around. We're pulling technology down from the big ones. You know, it started out with the ultralighters. And now you see it in Cirrus, you see it in a lot of light sports, and it saves hundreds of lives, and I think that is a truly wonderful thing. But there is a downside to it having gone mainstream, as I am now discovering in my work with Bat Ray, and that is that the major manufacturers of these things won't sell to non-OEM experimenters anymore, because they are now a big business. It's not economically reasonable for them, and there's a liability issue. And as an EAA community, I think that's something we need to find a solution for, so that us crazy experimenters can still experiment with the most safety possible. And if anyone knows of another manufacturer who is still selling LSA-sized BRS-style systems to individual builders, please let me know, because I do think that it's an important safety advance. It's something that was created by the experimental community for the experimental community and outgrew us, and it would be a shame if it ended up leaving us behind. So, a lot of attempts have been made to reduce the cost of conventional airplanes by improving manufacturing. For example, you know, the CB had, which this was derived from, had stamped metal skins with no ribs. The Amy Trojan, the ribs were on the outside, and they used symmetric airfoil so that they could pre-assemble the wing skins, and all four of them were identical and flat plate interchangeable tail surfaces. You know, the Rockwell 112 had beaded skins to get rid of the ribs. But what all of these things have in common is They cut the manufacturing cost a little bit, not enough to compete dramatically on price, and most of them cost just enough performance that the trade was not a favorable one, you know. So the airplanes, they sold some, but they weren't dramatically successful in the marketplace, and they didn't really fundamentally change the landscape. So now, improving conventional airplanes can only get us so far. So now what? Well, we take a page from one of the great design houses of the world, Monty Python, and now for something completely different. Interesting comparison here, and once again, I am not knocking my dear friend Randy Schlitter because this is a great airplane, but these two airplanes have the same engine. This one carries more load, flies faster, lands slower, and takes about half the time to build. Kind of cool. Because fundamentally, about the time I'm finished building my fuselage, I go flying and he's starting on building his wings. So, a different approach. What do we mean by that? The standard design practice is to use the wing body tail configuration. That's actually a very good configuration. One of the reasons it's survived so long is all of the effects are decoupled. I can change the wing size easily without changing the rest of the airplane. I can make the tail bigger or smaller to control stability problems. I can move the wing back and forth a little bit in design. So it's a very adaptable configuration that I can build successfully with very little beyond slide rule level calculations, which is a great thing, but it's kind of a monovariate approach. I'm looking at each thing individually. So now what happens if I take a look at everything together? Structures, aerodynamics, stability, control, all of it. There's the potential for very large advantages, and of course, one of the great advocates of all this was the great John K. Northrup. And if you want to read an utterly brilliant paper that shows somebody with just awesome insight into the fundamentals, find John Northrup's 1947 Wilbur Wright lecture to the Royal Aeronautical Society as an absolute tour de force as he describes why flying wings are a good idea. But his basic definition, which I'm going to expand just a little bit, is a type of airplane where all of the functions are disposed and accommodated within the outline of the airfoil itself. Another way to put it is there's nothing on that airplane that is not working for a living aerodynamically. By the way, I had this photo up on my wall in my dorm room when I was 17 years old. But if you generalize this idea from the pure flying wing to the idea of a configuration where everything lifts, you know, it opens up quite a collection of interesting possibilities. You know, from the classic B-49 flying wing to the NASA lifting bodies to the flying flapjack to the X-47B, which I had the honor of being the aero designer on. Just a little tidbit to show you how cool these kinds of configurations are. That airplane has an aspect ratio of 4.5 and a max L over D of over 19. Yeah, I'm very proud of that. But it's more the architecture of the airplane than the brilliance of Barnaby Wainfan that did that. So, however, we have a problem. You got to fit everything in the aforementioned airfoil. Mr. Northrup understood that. To wit, the dimensions of the human body may at times be the limiting factor. Well, guess what? On a 300,000-pound bomber, not a problem. On a light airplane, yeah. So if I try to apply the classical all-wing approach to a light airplane, the problem is that I have to get the air over and around two humans and back reconnected with a reasonable airfoil. I'm stuck with a chord of somewhere between 16 and 17 feet, minimum root chord. I can't do much less than that. Well, the problem is, if I take that and I apply it to the classic Northrop flying wing planform like the N9M, I will end up with an airplane with an 80-foot span and 905 square feet of wing area for a 2-seat airplane. It's a bit much, even for an ultralight, right? So what do? Start cutting off the wingtips till you end up here. And it drives you to an aspect ratio of somewhere between 1.5 and 2. Now, Fasmobile was actually 1.0 because it was such a light airplane that I couldn't drive the wing loading. You know, if I'd gone up to aspect ratio 2, the wing loading would have been even lower than it was. Well, guess what? There's historical precedent for that. You know, one of the really interesting things in design is if you see something that defies conventional wisdom, and it only happens once, maybe it's an anomaly, maybe they're a liar. If it happens multiple times, it's trying to tell you something about some fundamental physics, and it's really interesting to go figure out what that fundamental physics is. And this is kind of the journey I went on. I got started really down this journey in 1972 when I saw a picture of that airplane on the cover of Air Progress, July 1972. I still have that magazine. It changed my life. But you know, you take a look, and you know, before the Dyke Delta, there was the Arabs, which were built in the 1930s, which actually had very good performance for their time. And then one of my all-time favorite airplanes ever, the Vulcan. You know, which with an aspect ratio of 3.5 has a better range payload performance than either a B-47 or a B-52. Just amazing airplane. I had the very good fortune to see one fly once, and just, man, that's a religious experience. But, you know, I didn't invent all of this. A lot of people have been playing with this. There have been a lot of interesting airplanes built. There's a fellow in Australia named David Rowe, who I would dearly love to meet, who's on useless flying object number 4 now, because he keeps building circular airplanes. His latest one is retractable landing gear, and he's now starting on one with 2 seats. But a lot of interesting airplanes. All of these airplanes flew quite well and had pretty good performance. So there's something there. So what does this configuration do for us in the world of personal airplanes? Well, it's got a lot of things going for it. It's structurally light because it's a short, thick truss. The load paths are nice. There's not a lot of load in the spar members. Simple structure. Very benign flying qualities. The Fasmobile at least won't stall. You can sit there at full aft stick and it'll mush and settle at about 1,000 feet a minute and maintain fully under control, and you can even roll it back and forth with the elevons. Which means the airplane is as close to immune to stall spin as it's reasonable to have within physics. I do not believe I can make the claim that somebody won't figure out how to do it, but you have to work at it. Because the root chord is so large, it's very tolerant of center of gravity travel. When I flew the Fasmobile to Oshkosh, you know, I was bringing 2-stroke oil along because I had a Rotax 503 engine. And so I put 20 pints of 2-stroke oil in a rucksack, tied it to the rear bulkhead, which was 3 feet behind the CG. And the position of my trim moved 1/4 of an inch, and that's the only way I could tell that I had moved the CG that much. Pretty neat. And 2 other things that are really neat about this. The pilot is in the middle of a cage. I'm actually going to move over to the picture. So the pilot is 6 or 7 feet from anything that's going to hit anything. You got lots of crush space around you. And by the way, you have a very roomy cabin. I can sit in the seat of the Fasmobile and put both hands straight out and not touch the windows. So you have the ability to put shoulder room in there. So, you know, once you've done it, once you come up with all these great thoughts, you got to build it. And of course, you know, it's the 31st anniversary of that. You know, and as a long-time EAAer, it doesn't get any better than that. You know, I got my first issue of Sport Aviation when I was 16 years old and said, someday. Well, it took me 20-something years after that day, but I did it. And if fate is kind, in a couple of years, we'll do it again. But, you know, what was the objective of this project? Well, you know, stop talking and start testing. And in some respects, And by the way, these last two, mission accomplished. The origin story, one of the origin stories of the Fasmobile is probably around 1986 or 87. I was walking the line here at Oshkosh one evening, and I came upon the most god-awful airplane I had ever seen. It was a little white biplane, and it was kind of lumpy, and it was kind of dirty, and it literally had a canopy made of pieces of Lexan held together with sheet metal screws. And I was standing there thinking uncharitable thoughts about this person's airplane, and then the little demon whispered in my ear, yeah, but his airplane is finished flying and on the line at Oshkosh, and yours is a drawing on a quad pad. Get to work, right? He finished his airplane, by God, and he flew it, and good for him. But you know, the whole UFO report thing, I'm pretty sure we created a bunch because I flew over the interstates the whole way. And one story from the early flight tests of the airplane, a friend of mine told me this. We were flying out of Chino Airport. You know, Chino is in the middle of the world's largest dairy preserve, so the liquid in the ditches next to the roads is not particularly pleasant. I was orbiting overhead, and apparently, because my friend was following this guy, a pickup truck was coming down the airport periphery road, and I came by, and the guy was looking out the window, like, what is that? And then I turned, and then he turned, and the road didn't. So he ended up in the ditch from watching the airplane. So now on to some technical details. Here's the answer to the question. It has nothing to do with the F-117, which was still secret at the time. And, you know, various people have asked us, did you steal the design from Lockheed? Well, my friend Peter Lurd, who put the first couple of flights on this airplane, came up with the right answer for that. He said, yes, we did. It's a nose wheel chock for a C5. Next question, doesn't the airflow separate at the facets? Well, here's wind tunnel tough pictures. No, it doesn't. Now you'll notice here I had a few vortex generators up at the top. Turns out we didn't actually need them on this. I just happened to do the tufts on this run. And if you look very carefully at this, you can see this is a 30 degrees angle of attack. You can see the flue is mostly still attached, except that you can see the beginnings of a leading edge vortex and the beginnings of a little bit of separation just inboard of the fin. And what's interesting is when you fly the airplane to extreme angle of attack, you can actually hear that flow separation tapping on the fin, but the airplane stays completely controllable. So 1994, here we are at Oshkosh, day one, right outside the Brown Arch. One day later, I'm out in the flyby pattern, and I think we got the Dead Grass Award for that year. You know, by the end of, I mean, you can even see the propeller and the hatch. You know, by the end of the show, this was about a 4-inch deep trench. So great fun. I mean, it's a wonderful thing to bring your own creation to Oshkosh, you know, regardless of whether it's radical or just a beautifully built conventional airplane. It's something everybody should do once. So, but what did we actually achieve in terms of physical capability of this airplane? These are the actual numbers. It weighed 370 pounds empty on the ramp. And that included the BRS parachute, which weighs 26 pounds. That's the zero fuel weight of the airplane. We flew it as high as 740 pounds, so we were carrying 340 pounds of useful load on 46 horsepower at close to 80 knots cruise. Because my actual block time over the 2,500 miles from Chino to Oshkosh was 77 knots, and that includes the pattern. You know, I calculate on the basis of straight line. So it's probably about 80 knot cruise. And, you know, we did pace the airplane with another airplane with calibrated airspeed indicator at 4,000 feet, and we got 102 knots. And that's with a Rotax 503 and a fixed pitch propeller, no wheel pants. There's probably another 5 knots in it if I had cleaned up the gear and the cooling. So I would count that as a successful experiment. And then in 1995, when the engine failed on me at a few hundred feet, I somewhat more dramatically than intended, proved the validity of all those other safety considerations. Because when all the noise stopped, I was sitting on the periphery of Blythe Airport with a broken landing gear, and I was able to get out of the airplane completely intact and go, crap, I broke my airplane. And by the way, just to give you an idea of the virtue of low landing speed, I paced it off looking at the marks in the dirt. It was 75 feet from where my wheels touched the ground to where the airplane stopped. That's how effective it was at getting rid of the energy right before touchdown. So, project continues. Now in the late 1990s, I'm working on a two-seater called FMX-5. That got as far as a wind tunnel test, although it also turned into a glider UAV that's still being flown by a company called Near Space Corporation out of Tillamook, Oregon. They're building these at about 1/3 scale. They're launching them from high-altitude balloons to bring payloads back. And we've actually had 2 of them dive supersonic and recover when the control systems malfunction, which is not what I designed it to do. But some interesting data from that wind tunnel test. This is lift coefficient versus angle of attack. Now, a normal light airplane stalls at between 15 and 16 degrees. So you approach it maybe 10, you've got maybe 3 to 5 degrees angle of attack margin to landing, to stall when you're approaching to land. This airplane, the lift curve is completely flat. We never did find max lift because the angle of the support system would only go to 40 degrees. So you can sit there at full aft stick and still be basically at max lift. I'm approaching here, roughly, a little higher angle of attack than a conventional airplane, but I've got, literally even to the first break in the curve, I've got 8-10 degrees angle of attack and margin, and even if I treat that as max lift, I've got 15 to 20 degrees angle of attack margin. That's a lot of safety margin right there. Now, the airplane has another really interesting characteristic. This is pitching moment as a function of angle of attack. Nose up, nose down. So here's constant elevon deflection. Notice that as I get to about 20 to 25 degrees, I've got a nose down pitching moment break. This is full aft stick, so you cannot trim that airplane above 25 degrees. So it's self-angle of attack limiting in very much the same way as a canard. Now, what does that mean when we go back to the curve of doom? If I stall my Cessna 150 and smack into the ground, it's gonna kill me. If I hold full aft stick in my low aspect ratio airplane, I'm gonna mush into the ground at 45 miles an hour landing gear first, with it buffeting madly and telling me it doesn't like it all the way to the thump. And then I will walk away and realize how dumb I was and go build another airplane. Now, in 2004, we did a NASA study, a study for NASA. If you go into the NASA technical report server and search my name, you can download this contractor report. I won't go into any detail about it. You can also download it from my website, which is wainfan.co. And it's actually, if you want to get into the full mathematical geekery of what I am going to cover in the next few slides, it's in that report. That way we don't have to go through all of it here at Oshkosh. So the question is, why does it work? I mean, the demonstration is successful. The airplane has good performance, good safety. But what's the physics of this? Because conventional wisdom says that low aspect ratio is inefficient. But is it really? Well, depends on what you mean by efficient. Because what I care about is transport efficiency. And transport efficiency, put simply, is my goal is to transport an object or something from point A to point B. The real question I care about is how much fuel I burn to do that, which goes directly to what is the drag that I have to overcome while I'm doing it, or what is the thrust I have to generate to make the airplane fly that trajectory. So there's a lot of things that go into that. Because, you know, except for sailplanes, you know, the cost of transporting the vehicle itself from point A to point B is overhead. I don't care about it. Sailplanes, you know, they're racers. They only care about doing the trajectory. They don't leave any cargo behind. So, but there's aerodynamics, structures, and propulsion all go into it. Now, the second law of applied aerodynamics is it's always propulsion's fault, but the way I look at that is the efficiency of the propulsion system is beyond my control as an aero designer. I will buy the best engine and propeller I can, and I got to live with it. But I can affect the structural weight fraction, and I can affect the aerodynamic performance, and the way they play together is really important, and this is where the interesting insight comes. Because if I look at transport efficiency, what it really is payload to drag ratio. How much drag am I making per pound of payload? Never mind the weight of the airplane. For the whole system, I mean, I'm dragging the airplane along with me. Now, what's really interesting is it comes down to this really simple number, that it's the payload fraction times the lift to drag ratio. And that's a beautifully simple parameter that you can optimize. And it's really interesting because what it lets you do is trade structural efficiency against aerodynamic efficiency directly. And so with that as background, and once again, did I invent this idea? No, I did not. There's this really cool paper, and here's the citation. This airplane, believe it or not, is the beginning of Airbus Industries. Handley Page Aircraft was looking at doing a flying wing airliner with people in the wings. And what they discovered, much to their surprise, was that their initial design, which was higher aspect ratio, wasn't showing any more efficiency than a DC-9-ish conventional airplane. And Mr. Lee realized that it was because it had too much wetted area. So he just started cutting the wingtips off. And the efficiency kept getting better and better and better and better. And he said, okay, this is kind of crude because it's constant chord blocky wings with a nose sticking out. So he said, what if we blended it and ended up with this airplane, which to me looks like the Fisher-Price version of a Concorde. But nonetheless, his math is somewhat convoluted in a very British sort of way, but it's the same basic idea that when you get the density of the airplane up so that you have a lot of payload per unit wetted area, the overall efficiency goes up. And this is really a very good paper that goes into the physics of that. So let's look at each of those components. What I care about is structural weight fraction and L over D. Well, as we've already said, low aspect ratio shapes are structurally very efficient. So what this is data taken from actual airplanes. Every dot on this plot is a real airplane, and curve fit. And this is the payload fraction. So this is the useful load over the gross weight. There's Fasmobile. One of these is a Dyke Delta. Some of these are airplanes from that low aspect ratio chart. And what's interesting is if you look down at the low aspect ratio end, the all-wing, all-lifting airplanes do really well on payload fraction. These are wing body tail airplanes. They do a lot worse. So on that payload over gross weight piece of the transport efficiency equation, these things do really, really well. But, conventional wisdom tells us the L over D of a low aspect ratio airplane is lower than the L over D of a high aspect ratio airplane. Well, it's true, but it may not be as bad as you think. Because if we go through all the math here, what we discover is lift to drag ratio is only dependent on a few things. Span efficiency, wetted area, skin friction coefficient. That's the whole world. I love the ability to take a complex problem down to something simple like this. I've got 4 parameters. I can look at any configuration and say which one of these are you improving or hurting. So let's look at it. This is data once again from the FMX5 wind tunnel test. This is a span efficiency 0.9 parabolic polar. These are the actual test points. That's a lot better than a conventional low-wing airplane. They tend to run around 0.7, 0.75. So what does that tell me? It doesn't have a lot of span, but the span it uses up very effectively. What does that mean? That for a given total lift, the induced drag is a little lower than you would expect for a conventional configuration for that span. However, the other one is really interesting, and that is because of the large chord, I'm at high Reynolds number. High Reynolds number drops the skin friction coefficient. So what you discover is that, yes, I've got a bunch of extra wetted area, but I'm paying 18 to 20% less per square foot of wetted area because Fasmobile, for example, is flying at a Reynolds number of about 14 million, while a conventional airplane on the wing is flying at a Reynolds number of about 4 million. And this is an exponential function with Reynolds number. So what it says is I've got some interesting characteristics of these configurations that mitigate some of the apparent penalties. And it turns out it does it just enough that if you do it right, you come out ahead. Which is what this chart says. So let's look at actual test data. Well, let's compare my beloved Cessna 150 with the Fasmobile. And this is really interesting to me in the difference between a designer who looks at multivariate and a specialist who looks monovariate. And I'm an aero guy, so I can say that. So here's lift to drag ratio as a function of airspeed. Blue is the 150, green is the Fasmobile. Aero guy looks at that and says, your configuration sucks. L over D is worse. Now, I put the structural weight fraction in, I look at payload to drag ratio as a function of speed, and lo and behold, when I get out into the cruise speed age, the airplanes are actually almost equivalent and the Fasmobile's a little better, in spite of the fact that the L over D is that much lower. And all of the other benefits are still there, cost, safety, all of that. And as I said earlier, Fasmobile was a suboptimally low aspect ratio just because it was such a light airplane. Well, and once again, some of this is changing as of yesterday because saints be praised, Mosaic is now real. But FMX5 was designed pre-LSA, and I started saying, okay, what about an LSA version? And the NASA study was focused on minimizing cost, not necessarily the rest. So I said, okay, I never got to build FMX5, so I'm going to do another iteration. This is FMX7, now known as the Bat Ray. Here's a wind tunnel model of it. This is what I am now building in Independence, Oregon. And it was designed to the light sport rules, which I have now conveniently crossed out because Mosaic has eliminated a lot of this. However, we still had the clean stall speed, 120 knots, and the old 1320 gross weight was a severe limiter. So, in the development, we did do about a 20% RC model, instrumented so we could get real data. It flew beautifully. I was able to get about 60 hours of wind tunnel testing at the Cal Poly Pomona. I was able to sponsor student projects and not only, by the way, get a lot of good wind tunnel data, but I also was able to find 2 or 3 amazing new young employees for my company. I work for Northrop Grumman. And one of the things I absolutely love is one of the students who was on this project was actually my test engineer on the last test I did at Northrop for an advanced fighter. So you gotta love that. Just, some tough eye candy. Once again, you can see, this is roughly approach angle of attack. You can see the leading edge vortex beginning to form. And one of the things I've kind of wanted to try, partially because it's cool and partially because it has real advantages, is the inverted V-tail. The tails brace themselves, which is nice structurally. And then, as you see here, I've got the rudders towed out, so I can actually do the pitch trim function with the rudders instead of with the trim flat, like on the Fasmobile. And that means I don't have to decamber the wing to trim it. So doing it that way drops my approach speed by a couple of knots. Now, between FMX5 and FMX7, I actually learned a little bit more in aero about refining the configuration. So here are the lift curve slopes for the FMX7. And you can see, first of all, the CL max is about 20% higher than the FMX5. And once again, it has this beautiful flat top lift curve. And once again, we hit the limit of the wind tunnel support system without finding the actual stall. So this airplane will approach at about 10 degrees angle of attack at about 50 knots. And I've got 20 degrees angle of attack margin. And just like FMX5, it's got that nice stable nose down brake at high angle of attack. That's 2 elevon deflections. So, you know, what I'm going to present now is, obviously I haven't finished the airplane yet, so this is based on test data and other data. It's estimates, but it's not guesses. It's database stuff. These are the sources of all the data. Weight is the hardest one to predict. So I did it 3 ways. I did a parametric reversion, and it's in that NASA report on low aspect ratio airplanes. Payload fraction is a function of aspect ratio. Then I did a deconstruction of the Fasmobile where I know the actual weights. I said, okay, I'm going to take the Fasmobile, I'm going to take the Rotex 503 off and put my Jabiru 3300 on. I'm going to add an extra seat. I'm going to increase the structural weight by this much percent because of the, you know, increased size of the airplane. I'm going to, strengthen the landing gear increase the landing gear proportional to the gross weight of the airplane. And then I also was able to get weight data from the original Dyke Delta and go through the same sort of an exercise of take stuff off, put some on to morph one to the other. Now, I got weight estimates anywhere from 516 pounds empty to 650. If I can get anywhere near 520 pound empty weight, I will be beyond ecstatic. It ain't gonna happen, but it would be nice. For all of my design calculations, I took the heaviest gross weight that I could estimate, which is 650, heaviest empty weight, and that's what I'm using as a basis for everything here. Now, 650 pound empty weight gives you 670 pounds of useful load within the old Light Sport 1320 gross weight. I actually designed the airplane to 1,400 pounds, which means if it comes anywhere near making its numbers, I'm going to have 750 pounds of useful load in a 120 horsepower two-place airplane. Now, you want to really warp your mind. Imagine putting a 200-pound pilot in that airplane, making the rest gas, but fly best a specific range. It's about 1,500 miles, but it would hurt. So, comparisons with existing airplanes, and once again, these are now the new Mosaic compliant numbers. Cessna 150, 515 pounds of useful load. And that's not Light Sport, that's good old Cessna 150. The Diamond Eclipse, notice the empty weight's even higher, and it doesn't have that much more useful load, which is interesting. It shows that the composite airplane isn't really that significantly lighter. And here's what we're looking at for this airplane. And this gets us back to that weight fraction. This is the Diamond versus the Bat Ray, where the green is the useful load, the gray is the empty weight, and taking up to gross. And you can see I'm using a whole lot more empty weight of airplane to move a good bit less payload around. We buy airplanes by the pound. I'm buying a lot less pounds of empty, 200 plus less pounds of empty weight. So let's go back now to efficiency, transport efficiency. Where do we get? Well, now it's really interesting. Now I look at L over D, and because I've gotten to the point where I've refined the Bat Ray a little bit, and its aspect ratio is about 1.8, which is about right in the sweet spot for low aspect ratio airplanes. Right, the Dyke Delta is 2, by the way, just so you know. John was right. Well, now, if the Aero guy is comparing the Bat Ray to the 150, he's going, hey, you did pretty good. But oh, by the way, those guys improving the conventional airplanes still beat you. So the conclusion is still, your low aspect ratio airplane sucks. Its L over D is much worse than my pretty composite airplane everywhere. And so I say, okay, let's talk. Let's look at the actual power required to fly at gross weight. Well, the 150, yeah, it's not a paragon of low drag, right? But now what's really interesting is if I look at the D820 and the Bat Ray, in the cruise speed range, the power required is almost identical. but the battery is carrying 150 to 200 pounds more useful load. Which means when I finally get to the transport efficiency, it wins. And one of the interesting factors is, one of the reasons this does this, if you go back to the L over D curves, which you will see that the low aspect ratio airplane actually hits its best L over D at a somewhat higher speed. It's shifted to a lower lift coefficient. Now, this is not quite as dramatic as it would be if they were the same wing loading. But fundamentally, what you take a look at is you see here that, you know, everywhere above about any speed I'd actually want to cruise, the low aspect ratio airplane is actually giving a significantly better cruise efficiency. And we've done some preliminary design studies on something we're calling Huge Mobile, which is basically a Cessna Caravan replacement. And rough estimate is I can cut the fuel burn per pound mile in half by using this approach. But what about the other performance? Rate of climb. Remember, because I'm holding payload constant and I've got a lot less empty weight, that means at a given power, my power to weight is better. The airplane accelerates better, it gets more excess power, and the net result is here's rate of climb as a function of altitude, max rate of climb. If this thing hits its numbers, I'm going to be able to take off, rotate, peg about 85 knots and climb somewhere around 1,600 feet a minute. And one of the neat things about it is because the sweet spot is at a higher airspeed on a cross country, it actually reduces my time even more, because instead of taking off, pegging like 70 knots and dragging my way up at 500 feet a minute, I take off, peg the airspeed indicator at the cruise speed of my 150, and I'm still climbing over 1,000 feet a minute and getting across the map. And then, you know, I can settle down. I mean, so the cruise time on these things is awesome. Takeoff is another place where the combination of low wing loading and high thrust to weight helps. So if we go down here, and bat ray will rotate at about 400 feet from brake release, and 50-foot obstacle about 600 feet down the runway. When the bat ray's crossing the 50-foot obstacle, the Cessna 150 pilot is thinking I should rotate soon. And the Diamond pilot has another 500 feet to roll before he's even thinking about it. Kind of cool. Approach and landing. I've got a stall-resistant low-wing loading airplane. So minimum airspeed on the bat ray is going to be below 40 knots. Which means I'm going to approach it about 50 knots, roll less than 400 feet on touchdown if I do it all right. Land in less than 1,000 feet over a 50-foot obstacle. And that beats the heck out of the conventional airplanes. About 5 pounds per square foot. So here's first order performance. So under the 1,400 pound gross weight, which is what I really designed the airplane to, because I was going to register mine as an EAB. 750 pounds of useful load, 120 knot. Actually, the cruise speed would be a little bit higher than that. I didn't have a chance to revive, because the 120 knots is with the prop pitch down to limit the speed. So here's kind of what the structure looks like. Lots and lots of aluminum tubes. One of the cool things I'll show you a little bit about it is we are building this. A chapter mate of mine, a good friend named Robert Haynes, he's got a company called Workbench CNC. He has a homemade 3-axis CNC system with routers, and we are NCing all the parts for this thing. And it's cool because the parts come off with the copes perfectly cut, the gussets perfectly cut, all of the pilot holes in there. And I'll give you a little taste of the precision you get out of that. So just an update from here. People ask about the Fasmobile Replica that is being made. I don't have charts on it this year, but he's down to finishing the cowling before we're ready for fast taxi. The airplane's otherwise complete. And here I am in a cage of my own making. As I said, we're NCing the parts. So, they come out with the copes already cut with all the pilot holes in both the tubes and the gussets. Robert's even gotten to the point, you gotta love the EAA spirit, right? Before we actually do the pass over the metal to cut the gussets, he puts a Sharpie in the tool holder and it numbers all of the gussets first. So this is what the airplane looks like. Now, these pictures are a little old. It's come a bit further. I would estimate the assembly on the primary structure to be somewhere between 75 and 80%. Haven't started on the detail systems integration yet, so there's a lot of work yet to go, but I'm making good progress. I'm in the process of adapting an engine mount from another airplane. We're going to be welding some additional tubes to this to chase the loads out to that corner. I've purchased my motor. I have a new Jabiru 3300 and a lovely Sensenik composite ground adjustable prop. So, I've got that sorted and I'm working regularly on it. Now, one other thing I wanted to put in this talk because I think it's cool, it's just a little sidelight, is I've been using a lot of 3D printing for tooling and jigging and mock-up. So, for example, here, I needed to hold a couple of tubes in parallel at the right spacing while I riveted up the gusset. So I was able to create this clamp. And then if you look here, it's a little hard to see, but I have a set of clips that clip around the tube that have a plane that's tangent to the tube so that I can clamp a gusset in and drill holes if I need to. And it's set, I have edges on those clips that index everything so I can guarantee that the holes go down the center line on the tube even in two directions every time. And it's a really cool capability to have. And then this is my favorite invention with 3D printing. You know how we all have level apps on our phones, but how do you keep your phone on the, it's a wobbly case. So this is a repeatable phone holder and the bottom is both a flat plane and a V-block. Using this, I was able to get you an idea of what kind of precision Robert's system creates. You see all the cross-ship bulkheads in the main truss? Clecoed them up, sitting literally on just jack stands. No level table or anything. Clecoed it up, got the Cleco seated. Every single cross-ship tube is parallel to within 1/10 of a degree. Gotta love that. Think about how long that would take to achieve if you were doing it the old school way, the bandsaw and file. I'm not sure I frankly could have built this airplane without it. The other thing that I'm using it for is to mock up metal parts before you make the metal parts. These are landing gear attach lugs and so forth. But if you can design it up in CAD and make it in plastic and make it fit, you can iterate that 2 or 3 times for real and then make one metal part. And likewise here, this is just a spacer. I'm rigging the landing gear here. So you can see it's got a little loop that goes around the tube and then a flat plane. So by putting 2 of those in 2 different places, I'm able to rig the gear in order to install it. And so once again, I've been making templates of various sorts to do that. And really neat technology, helps you do a lot of things. This gives you an idea of the kind of precision we're getting with CNC cutting. This is where the tubes butt together at the leading edge at the break where the outer panel comes off. Notice the gap. This is the trailing edge 14 feet away from it. We are holding to the thickness of the tubing wall in 14 feet. So we're holding 35 thousandths of an inch in 14 feet with a homemade CNC in Cleco. So, one of the things I love about this project is this really intriguing mix of old school and modern. It's an aluminum tube, pop riveted, fabric covered airframe being made on computer controlled, homemade NC machinery with 3D printed templates and parts in it. So, you know, we're kind of in the grand spirit of EAA, I think, grabbing a little bit of the best of everything to cook an entirely different dish for us all. So, final thoughts. I think we got something here. I'm going to continue the experiment for as long as I can. I estimate probably 1.5 to 2 years to first flight right now. I'm working steadily on it. But if you take a look at the advantage of this that are intrinsic in the fundamental physics of this configuration, I think you have the potential to really create something great. And with that, I'm going to thank you for your attention and take questions. If you want to find my website, I've also got a newsletter out here at this Substack. So if you follow that, I'm posting periodic updates. A lot of the stuff that I've shown here, pictures and so forth, is there. And okay, let's get to some questions. Yeah?
Why does it seem to have a low coefficient, maximum coefficient of lift?
Why does it seem to have a low coefficient of maximum coefficient of lift? Because it does have a low coefficient maximum of lift, but it has a low wing loading to compensate. That is one of the things about doing tailless airplanes. They don't trim flaps, and you can't put a huge amount of camber in. So CLmax is lower than a conventional aft tail airplane. However, what's really interesting is when you compute CLmax on an airplane with a tail, you ignore the area of the tail. Try adding the tail to the reference area and you'll discover the CLmax isn't that different. But
Why can't you put more camber in?
because you can't trim it. And also, I'm cambering it for cruise. And I don't need to. I mean, with the CLmax I've got, you know, I've got a 38 knot stall and it'll still get on the high side of 120 knots. How much more do I need? Yes, sir.
I thought with that much extra useful load, this is potentially interesting all electric.
With that much useful load, it potentially interesting all electric. Maybe to somebody else. But all snark aside, with that extra useful load, it certainly has more potential to carry the excess weight of the batteries with the same useful load. In other words, if I take the fuel weight and the battery weight and I go let it drop down to, let's say, 600 pounds of useful loaders or 550, I can carry an extra 100 pounds of batteries or 150 pounds of batteries. The other thing some people have been looking at is it's got tons of volume. So some of the people playing with hydrogen fuel are looking at that path too. You know, so fundamentally, if I have something that's more efficient at transporting weight around, that just gives me a lot more interesting possibilities of what do I use that weight for. So yeah, as compared to a conventional wing-body tail airplane with the same load in the cabin, crew and baggage, yeah, I could probably carry about 100 pounds more batteries, and that's a big deal, particularly right now. Yeah, Ed.
What would a 200 knot two-seater look like?
What would a 200 knot two-seater look like? It would look like a sleeked up like Delta. You know, fundamentally, if I were to do that airplane with, you know, about 160 horsepower, it would already be out in the 160 knot range somewhere. So if I was trying to go faster than that, I'd start trying to squeeze the wing loading up a little bit and squeeze, you know, wetted area down. You know, if you want to go maximum speed at very low altitude, this is not the right configuration. The right configuration for going very fast at very low altitude looks like a cruise missile. Of course, it lands like a cruise missile too, so there is that. Yes, sir.
If I were to slice the design of the faceted mobile up from the center line out to the tip, and
Yeah.
then draw a mean line between the upper and lower surface,
Yes.
do I get a camber?
Yes.
But I have no pitching moment?
You get camber, but you also get twist.
Oh, over the whole.
Yeah.
So the total system becomes zero pitching moment?
Yeah. And also, I'm cheating a little bit with reflexing the elevons, of course. So you know, fundamentally, if you were to make an equivalent airfoil out of it, you know, put the elevons in neutral position, you're carrying a little load on the elevon. I'm probably going to end up with sparrow strainers like on the Long Easy, you know, to adjust the float position of the elevons. On Fasmobile, I actually had some fixed tabs to adjust the float position of the elevons. But, you know, if you look at the bottom, there's a good bit of reflex aft camber on the bottom surface. But yes, there is some camber in there, and that's part of the advancement from Fasmobile to FMX7 is I've learned how to tune that up better than at the beginning. Yes, sir?
Have you figured out ingress and egress?
Have I figured out ingress and egress? Not much better than before. This one will have openable hatches on the sides. However, it's still, how do I get up there? How do I slither in? The Bat Ray prototype at least still has the floor hatches, and that'll be the primary. These will probably be for emergency egress. If I was going to go further, I would probably, because this is now not main structure, the main carry-through structure goes here, start making this, you know, a tilt up, tilt forward kind of thing. Then you get into issues of latches and things like that, because the problem with topside doors on a configuration like this is they're basically in the middle of your wing. If it pops open in flight, bad things happen. So you need either a plug door system or some kind of redundant latch system so that a single screw up doesn't cause you to lose the whole top of your wing in flight. Because if I do, then whatever solution we come to for the lack of availability of emergency parachute systems will become very, very important. So, yes, sir. Full span elevons? No, they're, it's 3-segment. The elevons start here and go to there. The center section, which is 7.5 feet wide, has its own independent little surface. And I'm actually going to be using a split flap under the belly and gearing that to the center trimmer to produce a zero pitching moment change, high lift and drag system. No, the outer portion is for pitch and roll. Let's give someone else first question. I'll get back to you guys. Yes, sir.
What's the depth of the fuselage and about what angle are the seats?
The cabin is 42 inches deep. Seats, I think, are inclined back 20 degrees. It's not sailplane-ish. The main spar here, right there, is 24 inches deep. You know, which gives you an idea why it's so structurally efficient, right? The main spars are 2 feet plus deep and only cantilevered out 7 feet. And 1/3 of the load is being carried inboard of the brake. So that's where the structural efficiency comes from. Interestingly enough, none of the structural members on this, except the attached fittings, are sized by material yield. They're all sized by buckling, by oiler buckling and skin stability. So you get into minimum gauge issues that you have to be very aware of when you're doing the structural design. Yeah. Say again?
Back in his time, they have to give old Nike a lot of
Do I have to give John Dyke a lot of credit? Absolutely. You know, John did a brilliant job of designing that airplane. And you know, what most people don't realize is he never stopped refining it. If you look at 555 Alpha in the museum, it's got leading edge cuffs that were not part of the original design. Let's see, how are we doing on time here? I think we are pretty much coming up on time. Is the next speaker in the vicinity? How long do you need? I don't want to step on your time. All right, very good. Sir?
Maximum flap deflection.
Maximum flap deflection? Do you mean my drag flap or my elevons?
Your drag flap.
In the wind tunnel, we tested it out to 60 degrees. I have not decided yet where I'm going to put the limits on the existing airplane.
The chord-wise position.
Right behind the CG, right behind the main gear.
Okay. Ideal aspect ratio of the lifting bodies of 1.8 to 1. You mentioned, I think, in that range.
1.5 to 2.5 is the sweet, you know, and that's detail dependent mission.
The wing loading.
Okay, I will be glad to have a long discussion with you later, sir, but let's give other people a chance to. Cruise lift coefficient, I think it's about 0.15 somewhere, because the wing loading is so low. You know, it really depends, because once I get the wheel pants on and pitch the prop up, it's going to go down because I'm going to be going faster. Anyone else? All right, then let's yield for the next speaker. Thank you so much for your attention. And If you want to talk further, we can meet out behind. Give me a moment to get my stuff together, retrieve all the phones and the tech and stuff, and I'll join you behind the tent for further discussions, or over there. Thanks again, folks.